Smiley.
So welcome back. Philip will be giving his third talk.
Okay, thank you. I hope the microphone's working. Okay, so the third talk, final talk in this lecture series, will be about the Ax-Lindemann Weierstrass theorem in an abelian variety. So as you recall, this is kind of the last ingredient in this proof sketch of the Money-Munford conjecture for abelian varieties. So let me state the theorem again. That I want to prove today. Let me also mention that this is a theorem that follows from a more general result, James Ax from the 1970s. And the proof I'm going to present is based on ideas of Jonathan Pila, also appearing in the work of Ilmo and Yafaev, to cover Shimura varieties. And also a lot of later work by people here in the audience. So, okay, what's the setup? As every day, I have an abelian variety of dimension g. I take the tangent space just to be c to the g, and fix a period lattice basis. So I can identify these two real vector spaces. And, this would just be a covering map here, a real analytic surjective group isomorphism whose kernel is exactly z to the n. Okay. So this is just, from this point of view, we don't see the complex structure at this point. But we will see it again today at one point at least. Okay, so and what we get from Pila-Wilke, from the application of Pila-Wilke, if we recall, if you have a subvariety of A, which is now kind of gone, we don't need it at this point anymore. If you have a subvariety of A that contains a torsion point of sufficiently large order in terms of the subvariety and all of the other fixed data, then a Galois conjugate of this torsion point will lie in the image of a real semi-algebraic curve under this uniformizing map. So remember we had a definable set here in R to the 2G coming just from the pre-image of this subvariety. And then we applied Pila-Wilke to count points, rational points on this subvariety, this definable set. These rational points correspond to elements in the Galois orbit of the torsion point downstairs. We found that there are a lot of rational points if the order is sufficiently large, and that there are so many, in fact, that, we get a conclusion from the Pila-Wilke theorem. The conclusion, again, is that, so there has to be some semi-algebraic curve going on. So there were some questions yesterday about this curve. So I'll write it down a bit more explicitly. So it's just the image of a semi-algebraic continuous map that's analytic on open 0, 1. So the image of this curve here on the uniformizing map will just be a priori a subset. It's going to be an infinite subset. And I'm taking the Zariski closure in the Zariski topology on it. So I claim that this is an irreducible subset in the Zariski topology, because we're analytic on open 0. But the claim of the theorem is that this is, in fact, a coset in A, in this abelian variety. So it's a translate of an algebraic subgroup, an abelian subvariety, by point, any point, not necessarily a torsion point. So in the application, it was a torsion point, but here it's any point. Okay, so this was yesterday, just to complete the logic. We saw that Axel Lindemann Weierstrass implies Money-Montfort. I already showed you how this works, modulo this structure theorem on the Weyl locus. Okay, so the goal today is going to be to apply Pilo-Wilke again, but in a different context to prove this theorem here. So that's the first goal today, and then afterwards is going to be a bit of outlook. Proof Axel Lindemann Weierstrass. And as a first step, so I already said that V here is an irreducible subvariety of A. And the main step in the proof of the theorem is the following proposition. The proposition says that the stabilizer of V is infinite. It has positive dimension. Let's put it that way. So the stabilizer, the same algebraic subgroup we saw yesterday. We're an ambient algebraic group. The stabilizer is an algebraic subgroup of A. Okay, so that's the main proposition to prove Axel Lindemann Weierstrass. Let me show you first how to deduce the theorem from the proposition. How does that work? That's a simple step. Okay, the zone of death has moved, but I can write here now, right? So, it's not translation, right? Okay, so we're in this setup here, and we first observe, okay, the stabilizer has positive dimension, and so we do kind of the same trick we did yesterday. We just mod out the stabilizer. And now we're in an abelian variety of smaller dimension. This is an abelian variety. And the dimension is now less than G because we modded out something of positive dimension. And of course, the idea is now just to use induction on the dimension. So Axel Lindemann Weierstrass. Well, so what happens if I mod out an abelian variety? So at the level of the tangent space, I get a linear map. And at the level of somehow this uniform, this real version of the tangent space, I also get a linear map. So the image of R here inside this smaller abelian variety will also be real semi-algebraic. So just put it this way.
Is it clear that the stabilizer is connected? Or maybe
It's not clear now.
so it might be a true
If you want to, you can take this, but I think this object is also, I guess it's also well-defined. But if you're not happy, you can also take the connected component here. In general, I don't think it's going to be connected. Okay, so I guess the point here is that if we uniform lines here, and then this will be, so there are two, this will,
No, no
yeah, I think it works either way. I'm also more comfortable with this. But it takes a bit more to write down. Okay, so if I look at this kind of situation, then this will also be of the same nature as this here. This will be somehow now uniformization map now attached to this smaller abelian variety of some other semi-algebraic curve. And so I just do kind of Axel Lindemann Weierstrass in this abelian variety, and it will tell us that this here is going to be a coset. But of course, we've modded out the stabilizer V, and so now it follows. This is purely formal that V is also a coset. Nay, because V is somehow fibrated by translates of the stabilizer. Okay. So that concludes this kind of deduction. It's an induction. Of course, I didn't do the induction base, but that's trivial in this case. Okay, so I'm going to prove this proposition as the next step, and that's where we're going to see Pila-Wilke a second time. Okay. All right. So I'm going to, at this point, at one point, we're going to have to remember the complex structure. So I'm going to kind of shift back and forth between these two worlds. You can imagine how it works. This isomorphism is given by this period basis. So we will identify R2G and CG via this basis. And I will just use whatever symbol is more convenient. I hope to convince you that I'm not cheating at this point. So the point is that, well, I think in the notation I did write no R here. So if I look at the preimage of this Zariski closure inside C to the G, well, I'll certainly get something that contains R, this semi-algebraic. This is just like, you can think of it as a germ of a curve. So it's not going to extend. So, but now we're in some affine space, right? Just in C to the G. And this is not a complex algebraic subset, something real algebraic, but I can take the Zariski closure of it with respect to the usual Zariski topology on C to the G, and it will still be contained in here because this guy here is complex analytic. So V is a subvariety, it's algebraic, and the uniformizing map is holomorphic. So the preimage will be complex analytic. And it will contain the Zariski closure here.
Sorry, I didn't understand this. I mean, it's not the case, but just assume R was infinitely many points.
Excuse me?
Can you explain again why the image of the Zariski closure is
Okay.
anything?
Maybe I'll explain it more in more detail because it's kind of a tricky step. So what is R again is some real semi-algebraic curve. So it's given by some real semi-algebraic maps. This. And now in this complex setting, well, the maps, if I use the isomorphism, I'm actually looking at this map here. Now I'm honestly inside C to the G because this is a period lattice basis. Now these here are algebraically dependent functions, gamma 1 to gamma 2G, because they define a semi-algebraic curve. Now they're locally analytic on open 0, 1. So I can extend them around each point in open 0, 1 to some holomorphic function on a small disk that goes beyond the real line. And they will remain algebraically dependent in this extension. Right. So the extension of this map to some small neighborhood of open 0, 1 will be complex analytic, and the coordinates here will somehow be transcendent degree at most 1. And it will define it. This will be a curve, actually. So that may be it's important. This is a curve, an algebraic curve. So they have transcendence degree over R is equal to 1 of these maps here. That's the curve condition coming from Pila-Wilke in the end. Okay. So this is the setup. So and then, yeah, it's contained in the complex analytic thing just by analytic continuation. Okay. So, but there could be other algebraic subsets. So this is an algebraic subset, and this you would not consider to be algebraic in general. If you have any random v, the preimage is going to be something quite analytic. But of course, if we look at the conclusion in hindsight, so a posteriori, we know that this is going to be something that looks like a linear space. But there could be additional algebraic sets contained between this one and this one here, sandwiched in between. So what I'm going to define is Z is the maximal algebraic subset. So now we're just in C to the G. That's sandwiched in between here and here. Right, this exists because this one is certainly algebraic, and I can just make it a maximal irreducible algebraic. And then if I impose irreducible also,
I could have similar ones.
A maximal is A
A.
maximal. I just fix any one. Okay. And so essentially what we're going to show is that the stabilizer of this one here is going to be of positive dimension. But now we're in a different algebraic group. Now we're in C to the G, which is just an additive. Okay, so now comes a simple observation. And that's something, again, I haven't pointed out yet, but I guess it's somehow implicit that this uniformizing map is periodic, right? So translation invariant. So the preimage of something will be just copies of it translated. This will be is period lattice translation invariant. That's an important point, but that's what I'm going to use now. So this is, quite straightforward observation, but it's quite critical now. So if I said I'm going to shift back and forth between the real and the complex world, so if because I eventually want to apply Pila-Wilke, and that's kind of attuned to the real setting. So I'll just take a period. This will be a period. You can think of it in the other coordinates as well. And then what happens if I translate my Z, this algebraic thing, by this period? Well, I'll be contained in the preimage of V translated by the period. But as I just said, this thing is translation invariant. This is the same thing.
Why do you put R on unit?
Because I want to be consistent with my notation. So this is, I'm
Here it wasn't
yeah. So this is kind of what I'm trying to do with my notation. Identify R to the 2G with C to the 2G because I chose this period basis. And at one point we're going to have to go back to C R to the 2G to do Pila-Wilke. That's just a point, I think. Okay, so, but we want something periodic. We have something periodic, and we also want something definable. And from this we conclude, well, this was our fundamental domain. I mean, you can do the same thing in the complex coordinates as well. And this will be contained in the preimage of V intersect 0, 1 to the 2G. And as you remember yesterday, it's not exactly the same set, but it's morally the same thing. This is going to be definable. It is definable in Rn. So this holds for all periods, right? And so what would we show? That every period, so this is somehow a lemma, but it just follows from this very basic observation that if I have a period, then the period is contained in the following set, which I'll call allographs y. And this is, now I wanted something definable, so I'm not going to write z to the 2g here, but r to the 2g, because I want, yeah, I can't speak of the integers in the minimal setting. So I'll make the set a bit larger. Okay, so I mean, this is just what I showed, just with x here instead of omega. Point is, the reason why I'm using r to the 2g, because this here is now a definable set. This is also definable in Rn. Quantifiers go to r to the 2g. Everything here is definable. Z is complex algebraic, and so it's going to be semi-algebraic in the real coordinates sense, and this, as we saw, is definable. So it's enough to work in Rn here because everything is compact. Right. And just for technical reasons, I'm going to add a second condition here, which is, I guess, formally necessary at this point, but which isn't much of a big deal. It doesn't hurt the definability at all. So I just want the translate, I'm going to draw a picture later. I want the translate of my z to intersect the fundamental domain in something of top dimension. Right, so this is maybe I should emphasize that this is always the dimension of a definable set here. This still remains definable if I impose this dimension, because somehow the dimension is defined using cell decomposition. Cell decomposition is definable. So this is part of the basic theory, if I have that condition. Okay, so in fact, I showed, if you forget about this for a moment, I showed that there are all these periods in this y. But I just have to make sure that this, I mean, all periods are in the set without the red. I just have to make sure that this extra condition here is also satisfied a lot, because then I'll find a lot of integral points in a set that's definable, then I can hope to apply pure Wilkie. So let me draw the promised picture. Horribly wrong. So typically what would happen is the following. So, so this is now r to the 2g, and try to draw in the lattice.
What is the statement of the lemma you started?
Ah, so the lemma is, okay, yeah, it's not actually, I think it was a lemma before, but now it's a definition. And yeah, so I'll restate it later. So if you forget about the red, the statement of what the lemma was that the periods are all contained in y, but I've added this extra condition here. We'll see it in a moment what that's all about. I'll draw that in my picture here. So this is the lattice. And inside this lattice, we have our z. And I kind of prepared. Show what can happen. This is our z. Remember, this is complex algebraic. So in particular, it's not going to be compact. It's infinite complex algebraic, so it's not going to be compact. And at that point, we use some slight information from complex geometry. And what do I want to count? I want to say something about this y. And I already mentioned that if I'm a period in z to the 2g, then I certainly satisfy the first condition. But what about the second one? So the dots here correspond to periods, and I'm marking all the dots where the intersection of the box here intersects the green curve in maximal dimension. So this would be a good box, right? Because this is kind of the translation of the fundamental domain I'm interested in. It meets the green curve, the dimension, the maximal dimension. This is a good box, so I'm marking it. This is a good box. I'm marking it as well. This is a good box. This is a good box. Now, is this a good box or not? It's not a good box because, well, the interval fundamental domain only contains like the lower left-hand part, but this is a good box. This is also not a good box here because the curve only meets in a point, so I don't want to count these two here. This is a good box, and this is a good box. So all the green dots here are contained in Y, and they're integral. Right, but how many of them are there? And as you can guess, so this Z here is, well, this is a basic fact. Z, by hypothesis, Z is infinite because it contains a real semi-algebraic curve or the image of something. Z is unbounded because it's a dimension at least one as a complex algebraic. So that's basic. Some complex geometry comes in here. So essentially what happens is, in this picture, Z will meet almost all of these boxes if I follow a path through Z going off to infinity. Right? So what I do, in fact, okay, here firmly it makes sense to work with the smooth locus of Z, and then the smooth locus of Z is connected because Z is irreducible, and you take a path on the smooth locus from any point you want, and you move out towards infinity, and then you show that you're going to pass through like a sequence of these boxes almost in adjacent order. There are some problems like here where you may miss the box because it doesn't hit it in maximal dimension, but then one of the adjacent boxes will. So pick a path in Z regular, going to infinity in any direction, and you'll pass through a lot of these good boxes. One passes. Boxes as you move out. How many boxes you move through? Well, the conservative estimate is that if you do t steps, like if you're distance t away from the origin, you'll hit roughly t boxes. That's kind of the conservative. Here is like a problem here, but that just affects like maybe a factor of half or something like that. So what is the conclusion of this process? Conclusion. We're counting points in Y for all t at least 1. The set of integral points in Y of height at most t. So that means after some your distance t away from the origin on your path towards infinity will be something that grows at least like t, almost linear. Or, yeah. Okay, and so this is a kind of case where we can apply Pilo-Wilke, because Pilo-Wilke gives us an upper bound for this, even for the rationals, if we exclude the transcendental locus. Exclude the algebraic locus. Okay, we'll apply Pilo-Wilke. And what does Pilo-Wilke tell us? So there has to be now some semi-algebraic curve lying in Y. Just C in Y, semi-algebraic curve, and also passing through one of the periods. And as I run along, so what does it mean to be in Y? That means for X in the curve, that just means that we have the second condition in red. Let's u X minus C, Z minus X meets Z in maximal dimension. So that means this is contained here in Z. Maximal condition, and because everything is algebraic, so if it intersects somehow in something of maximal dimension, then they have to be actually the same. Okay, that's from the, and we also get, well, that the translate here is contained completely inside. The preimage of V, the original set that we're interested in under the uniformizer. That holds for all X in C, and so somehow that means C is contained in the stabilizer in Z. So, conclusion. Blackboard.
Z minus X be some other reducible component of the unified of why Z minus X equals to Z?
Oh, okay, I just erased the critical point, the red thing. So what did it say? It said Z minus, the dimension of Z minus X cap 0, 1 to 2G is equal to the dimension of Z. And Z minus X, cap 0, 1 to 2G is contained in the preimage. Sorry, no, what I said is, this is wrong. Yeah, sorry about that. Okay. So what I actually want to say is conclude is this here. That Z minus X is contained in the uniformizer sorry, yeah, that was wrong. So what I want to say is because this here meets the fundamental domain in something of maximal dimension, and this maximal dimension thing is contained in the preimage, then so does the whole Z minus X have to be contained in the preimage. Right. That's now because of identity principle in complex geometry. Something of maximal dimension, this will contain an open subset of Z minus X, non-empty, and so Z minus X has to be in the preimage. So that's the conclusion I want to hit here, and that just means that Z minus the curve is contained, because this was true for all X in the curve, so the whole curve is contained. Now remember Now remember that the curve here was something real semi-algebraic, right? And so this here, it's not going to be real complex algebraic, but I can do the same trick as I did before. I can somehow extend this to something complex algebraic and create a curve out of it. And then I'll get, this difference will be a complex algebraic object contained in this preimage here. This here is contained in, let's call it Z minus C complex, which is completely contained. So this comes by complexification as the same trick I did before. You just extended some map parameterizing the curve to some small neighborhood of 0, 1 open.
So you took the just a maximal thing, but you should have taken it of a maximal dimension as well. No?
It's gonna, yeah, so that's exactly the point. This was, Z was maximal. And, okay, so at one point you may have to translate by a period. It comes from this here. I'm just going to assume that that period is 0 at this point. It doesn't make a difference. But we get this inclusion here. And this here is algebraic. And it contains Z. And because of maximality, it has to equal Z. Yeah, so this is at one point where the technical point is that, okay, the curve goes through a period, so in principle you have to translate here. To be completely precise, you have to translate by a period at one point. But that doesn't affect the algebraicity of the statement. Does that answer the question? Okay. So, so you get this here, maybe plus the period. But the important thing is that the stabilizer, so that means the stabilizer of Z has positive dimension. But Z, now we're in a different algebraic group. We're not in the abelian variety anymore. We're in the tangent space of the abelian variety. So this is going to be a vector, a linear subspace of C. It's definitely going to be connected now, but it's a linear subspace of dimension greater than 0. So now we're almost there, because we've now found something linear inside, inside the tangent space. That's what we're looking for. And now it's just a matter of putting things together. Let me see. It follows that. I just have to recall that, well, where were all these objects here? V was Z was contained in the preimage of V, and the image of Z is contained in V, and it's in fact already Zariski closed. So Zariski dense, so the Zariski closure is V. And from this we get immediately that the dimension of the stabilizer of V is also positive. And that's what we were looking for in the proposition. Because we get this one has positive dimension of stabilizer, and anything in the image of the stabilizer of Z under the uniformizing map will lie in the stabilizer of V. So we get positive dimensional stabilizer of V. That means V is somehow contains a lot of translates of abelian subvarieties, and that's what we quotient out in the proof that the proposition implies the theorem of Ax-Lindemann and Weierstrass. And that completes the proof of the proposition, or sketch of the proof.
So
this stab Z exactly a linear subspace, or is it like the stab Z contains a linear subspace?
Okay, stab C is an algebraic subgroup of C to the G.
Right.
And I think all algebraic subgroups of C to the G are linear subspace. Probably not necessary to use this fact at this point. It's important, what's important is that it's a positive dimensional algebraic subgroup of C to the G. That's a critical, in order to get that, the image of the elements will give you infinitely many elements in the stabilizer of the G.
Can you explain the role of Z space constraint? So, if it will be analytic, then how do you do it?
Z is algebraic. It's, at this point, we need, okay, so Z was taken as the maximal algebraic subset of this periodic thing containing the original curve. And at this step, we recognize this here as being,
I think I understand the argument. So, why it is important that it is algebraic? So, why it is so
if you're asking what happens if we take the maximal analytic subset. Let me see what happens then.
This is the uniform argument. This is just
That's unlikely to be the final one.
That's a point, yeah. We definitely used it in the theorem to apply Piola-Wilke. So the definition of why we had some, and yeah, there are analytic sets. For example, this one here is never definable.
Say why the stabilizer is positive dimension?
Because any element coming from this curve will give you an element in the stabilizer of Z. So you recognize by maximality that, well, there's an omega missing here, but by maximality, any point in this curve, the curve comes from the Piola-Wilke theorem. It's a real algebraic, semi-algebraic curve. And this is some kind of complexification of it. So you have infinitely many points in this curve. Any point you choose, if you translate your Z by this point, you'll get Z again. So everything in here, that will be translated, will lie in the stabilizer of the original algebraic set Z.
So you don't really need the omega, just having a curve.
Yeah, so you just need a curve, yeah. Further questions? Okay, so that concludes the proof of everything. Yes, please.
But how does the statement change if instead of starting with a curve you have a higher dimensional variety? Can you say something?
Can you repeat the question?
Now I mean, the statement says that if you have a curve, you take the image, you take the closure, and you get essentially that.
Yeah.
What happens if you have a higher dimensional variety? If you start with a higher dimensional thing?
It's the same thing. Because you can cover the higher dimensional thing, for example, by curves, and try to recover the theorem from that. Or maybe with a little more effort, you can actually prove it using the same method. I have to check. But the statement, the conclusion is the same. Any connected...
By the proposition, just need the positive dimensionality.
Yeah.
Then you just can
Yeah.
take a curve in your...
But I mean, the statement is really about just any maximal algebraic component, right? And that's how you prove it.
Yeah.
So it would be the same if you start
Yeah.
with something maximal containing the curve.
Okay. Any further questions?
Yeah, I don't know if
Yeah.
it's an ideal drawing question would be, so now we know model Piola-Wilke and another black box, that's my question, or the black box, so how involved is Serre's theorem?
Haha, okay. So the proof of Serre's theorem, okay, I just know the reference, I didn't read through this proof. So there are two, the reference, the second reference I mentioned is the theorem of Masser, and that uses techniques from transcendence theory. And in fact, there's a third approach to this kind of statement, which also uses the Pilo-Wilke counting theorem. So getting lower bounds for Galois orbits, that was a project started by Harry Schmidt, and then continued by Harry, by Gal Bignamidi, and by Andrei Yafaev, and that was an integral part in resolving the André-Oort conjecture for general Chmur varieties. So there's in fact now 3 you can apply the theorem. I don't know if it was written up for abelian varieties, but Harry definitely has a result for elliptic curves, which seems to be something that one could at least write up also for abelian. Did in your paper for Chmur varieties?
I think I even wrote it for abelian varieties.
Okay.
In some paper on foliations, but
Okay.
it was, I mean, same as what Harry did exactly.
Okay. So yeah, so you can now apply Pilo-Wilke 3 times in the proof of this theorem. But yes, back to your question. So Serre's, the proof of Serre's theorem, I can't say too much about the methods that go into there, except that some methods from transcendence theory developed by Massieu and Wüstholz and others can give some parts of Serre's theorem using these isogeny estimates. And it can give all parts that are relevant to all these applications.
Just a small comment, Phil. So
Yeah.
it's 3 applications, but the third one is not Pilo-Wilke, it's the Wilke conjecture. I mean,
Yes,
but it's 3
yeah,
applications,
okay.
Pilo-Wilke is already not.
Yeah. Okay, so maybe write this down. Also, yeah, so if Pilo-Wilke theorem was used, I used it twice, and then a generalization also will work of Gall, where you need polylog upper bounds. Then you can also attack the Galois orbits. And of course, I didn't say much about the Chmur variety situation here. I mean, the situation is more, of course, more difficult because the group acting is not going to be abelian. You have groups of infinite, of exponential growth, and somehow this path carting out argument doesn't really work that simply. You need volume estimates for some hyperbolic spaces. So that was all work done by Pilat, Zimmermann, Bakker, Klunor, Ulmer, Yafaev, and I hope I didn't forget anyone. Okay. So I have 15 more minutes, or if there's more questions, I can also take them now. And so maybe in the last 15 minutes, I wanted to say something about unlikely intersections. And perhaps a lot was already said by Fabrizio on Sunday. And as in the André-Oort setting, there's a version for abelian varieties, there's a version for multiplicative torus, there's a version for semi-abelian varieties, there's a version for Chmur varieties, and mixed Chmur varieties, and even beyond by recent work of Bruno Klingler. So I'm just going to also state the version for abelian varieties to keep the same context. So this is sometimes called the Silbert-Pink conjecture. Or conjecture on unlikely intersections. Namely, a priori it's something purely complex, an abelian variety. With your subvariety A, so it's reducible. And there's a condition on X. So in Monty-Montfort's condition is not the torsion coset. And here the condition is a bit stronger, or it is stronger. It's not contained in a proper algebraic subgroup. So in Monty-Montfort, it's not equal to a component of an algebraic subgroup, a proper algebraic subgroup. And here it's not equal to. It's not contained in a proper algebraic subgroup. And then the conclusion is that X cap A is not dense, not Zariski dense, except, well, what am I taking the union over here? A is an algebraic subgroup, H of A, and the dimension of H is less than the dimension of that A minus the dimension of X. And so the idea is that, well, just dimension theory, any irreducible component of this intersection has to have dimension at least this side minus this side. And so any intersection here is going to be unlikely. So you just think of two lines in three-dimensional space. They're not going to intersect so, with probability 1. But the lines here are somehow quite rigid because they're algebraic subgroups. They have arithmetic meaning in this context. So if you want to recover Monty-Mumford, I mean, you can just restrict to zero-dimensional algebraic subgroups. The condition is a bit stronger here than what you would expect in Monty-Mumford, but you can reduce to Monty-Mumford just by modding out a certain algebraic subgroup that we're working with in the quotient. Okay. So as I said, there are a lot of different versions of this conjecture. I'm not going to state them all, so you can just replace here mixture Moore variety. Instead of algebraic subgroup, you look at special subvarieties. But the proofs are very much different. So even though they're at the language of level, they sound similar, the methods are different. So I'll just make some historical remarks. First of all, I guess probably the first results going beyond like Monty-Mumford, where you really look at positive dimensional H. They go back to, in this setting, they go back to Bombieri, Masser, and Zanier. From end of last century, 1999. And so what they considered is curves over Q bar in the multiplicative group with a stronger condition than what you would expect here, but they get the correct conclusion and they can find this. And so it took some time then, but then Guillaume Morin, in 2008, did all curves in GM to the n over Q bar. And this one was then generalized the same year by Bombieri, Masser, Zanier to all curves over complex. And there's also a specialization kind of argument involved, as I very briefly alluded to in the first lecture, that you can reduce the complex case to the algebraic case, but it's not as easy as in the Monty-Mumford section. So this is a non-trivial step, and of course this theorem is also is non-trivial here. It's a very difficult theorem. Okay, and then there was a lot of work. Several authors. In the Abelian side, Pazzi and Carrizosa also worked in this setting, so some curves in some abelian varieties over Q bar, so everything is over Q bar here. And then Jonathan and myself, this was 2016, we did all curves in all A, I mean, at least if we're over Q bar. And this was just recently also generalized by Barolero, Fabrizio, and Gabriel Dill. This was published in 2022, I think, this year. And that's all curves over C and all A over C. So there was quite a big intermediate step here involved, namely this used version of the Ax-Shadwell theorem for mixed, for the universal family of abelian varieties. So there's a functional transcendence result going into this step here. So even passing from C to Q bar involved a lot of additional work, and again, an application of the Pila-Wilke theorem in this functional transcendence work that was also followed after work in the pure case by Pila, Zimmermann, and Mock. Okay. Let me also point out that this is somehow best possible in a quite strong sense. I mean, this condition here. So if you put in an equality here instead of a strict inequality, or allow just less or equal instead of strictly less, then it's completely false, the conclusion. This is also recent work. By Sebastian Terwich and Tom Scanlon. It proves that also in a more general setting than I have over there, that the dimension condition is optimal in a strong sense. So even so not only will, I mean, okay, in general, A could have not enough algebraic subgroups for there to make it be a difference if you replace equality here by, or strict inequality by equality. But in general, you have to expect this union to be even dense in the Euclidean topology if you don't have strict inequality here.
Maybe you should mention your recent work with Gao also, the relative setting.
Yeah, so yeah, I don't want to talk about everything because I only have 5 minutes left. So yes, there's a lot of work in the relative setting by a lot of different people, yes, including Gao, myself, and Dimitrov, and also Loris Kühne, that deals with families of abelian varieties. And that all started out with work of Umberto Zagni and David Masser, and also around the same time, 2008, where they did a first version of the so-called relative Manin-Montfort conjecture for curves. So instead of looking at a fixed abelian variety, you're looking at a family of abelian varieties. And so you have to adapt a few things here, but you also get a non-Zariski dense listing. Okay. Great. Okay, so the main, I guess, the main delta from here to here was that in the previous line of work, which was restricted to certain abelian varieties, it was relied on quite delicate height lower bounds that were not known in general abelian varieties. And so once this O-minimal machinery and the Pila-Wilke counting theorem became available, we no longer needed like these very delicate or almost best possible height lower bounds. And that was also the reason why we were able to treat all abelian varieties here, because we could work with, so the method is robust enough so that it can deal with certain height inequalities that are not optimal but just somehow have polynomial decay. Because remember in Pila-Wilke theorem, you can take any epsilon positive, so you can kind of compensate for any non-optimal bounds you get from somewhere else by just taking the epsilon smaller and smaller. So that was kind of the main, the reason why we were able to treat general abelian varieties. And then later, or at the same time, I think this was the work of Mauro Capuano, together with Agritko Bombieri.
No.
Oh, sorry.
Oh, the Capuano master.
Oh, sorry, yeah. Thanks. I had it written down correctly, but not in my head.
You said you don't want to pick.
Yeah. So this was part of her PhD thesis, to look at the original line of work in GM to the N. So this is also for Q bar, but it's kind of a also proof of concept work using Pila-Wilke. at least a version for Grassmannian. that we call it. Okay. So the main difficulty, I guess, the main open questions here. So the conjecture is open even over Q bar. The conjecture is known in dimension 1. It's known in dimension, or codimension 1, because that just corresponds, it reduces to Meyer-Mumford, and it's also known in codimension 2. So this is also work of Fabrizio and Gabriel Dill. So there's also a way to get around.
I think most was already in your paper.
Yeah, so over C it's due to your work, and over Q bar it's and so, but what's left is to do the intermediate dimension. So everything that's like beyond dimension 1, so dimension 2, if you're not codimension 1 or 2, then it's open. Open for surfaces. In general, and what part of the proof is missing? It's the Galois orbits, the lower bounds for Galois orbits. That's the hard part, and that was also the part, I guess the last part to be solved for the Audrey-Orr conjecture just very recently. And here it's still quite open, so we don't know what to do for surfaces in general. So there are partial results for certain surfaces that are in sufficiently nice general position, but for the general surface, we can't get the Galois orbit bounds, Galois orbit lower bounds that we need to apply the Pila-Wilke counting theorem to get it this direction. So in the curve case, we use the theorem of Raymond connected to the void inequality, but this is not available in higher dimension. Okay, thanks for your attention.
Any questions? More questions?
Is there any sort of, I don't know the details very well, but your work with Gao and Dimitrov, is there any chance of sort of applying that somehow to tackle the Gao orbits question? Like, is there a strategy there, or are you?
You mean, so that's kind of like the relative setting, right? So you have.
Well,
like
I want to understand you have a general height inequality,
Yeah,
and you use that to prove several
right.
incredible results. I'm just wondering, is there any sort of strategy to go from there to something like lower bound for Gao orbit or upper bound?
Well, there's a strategy in this setting to go from height upper bounds to upper bounds for Galois orbits, but the height inequalities that
So
one
from
would-
height upper bound, lower bounds for Gao orbits?
I misspoke, sorry, for height upper bounds to upper bound, sorry, from height upper bounds to lower bounds for Galois orbits, yeah.
Oh, there is.
There is a strategy, but the upper bounds are not available.
But if you had them, then you would have the lower bounds for Gao orbits?
Yeah. So, I mean, in precise, you'd have to make that precise, but if you have a, so for example, yes, I didn't write this down, but Raymond, he proved a height upper bound that if in the curve case, that if the point lies in the union of the intersection of the curve with the codimension 2 algebraic subgroups, then the height is bounded from above in function of the curve and the abelian variety and so on. This is what we use to get the Galois orbit lower bounds in a paper with Jonathan.
And is
So-
that some kind of isogeny thing, where you have a low degree field, small height, that you do some isogeny relation?
Well, so yeah, it's kind of, you can translate this kind of upper bound into, once you have an upper bound, you can produce a lot of points of very small heights, unusually small height, and then you need height lower bounds to get a lower bound for the degree, like these Lamer types. And that was, like in the pre-O minimal days, you needed the best possible kind of exponent in these lower bounds, because the method was very tight. And now with Pila-Wilke, you can get by with any exponent because you still have the epsilon to play around with. But you still need some kind of, I mean, you can get by with something worse than this, but for example, in recent work of Daw and Orr, this is the Shimura setting, they get height upper bounds where you have a dependency on the degree, and that's already enough because it's polynomial bound here.